Hi, in this video we're going to look at the exponential distribution. As I've said several times in previous videos, it generalizes to a gamma distribution, so we're going to talk about both. Let's just get right into the notation for the exponential distribution. I'm going to denote it by, the EXP is going to stand for exponential, and then this is going to be our notation for cap x following an exponential distribution with a parameter theta. There's only going to be one parameter theta. You can recognize, I'm going to just give you some punchlines here. You can recognize the exponential distribution by its density function this way. If the density function looks like this is an exponential function, if the density function is an exponential function, then you have an exponential distribution. The random variable follows an exponential distribution. The corresponding distribution function will be a 1 minus an e to the minus x over theta. So that's the distribution function. The expected value of the random variable is just going to be equal to the parameter, as we're using the parameter here, theta. So the expected value is going to be theta, and the variance of the distribution is going to be a theta squared. So those are some facts that you need to commit to memory with respect to the exponential distribution. And by the way, this distribution is probably one of the most often tested distributions on actuarial exams. If you've seen the material for exponential distribution before, you might have noticed that I might be using the parameter a little bit different way than what you might have seen it. Some folks, a lot of times statisticians, use a parameter lambda, and they would define the density function as a lambda e to the minus lambda x this way. I think it's pretty clear that they're using their lambda is our 1 over theta, so we're just plugging in a 1 over theta. Wherever we have a 1 over theta, they will be using a lambda for that. And so their distribution function, if they're going to use the parameter that way, is a 1 minus an e to the minus lambda times x. The expected value, if they're using the parameter lambda, the expected value when we use our parameter is theta, but if you look at the top middle equation there, the relationship between lambda and theta is that they're reciprocals of each other. And so if they're using a lambda as the parameter, then the expected value would be 1 over lambda, and the variance would be the square of 1 over lambda, or 1 over lambda squared. There are reasons that you'll see later on when you're studying for the short-term actuarial math material that I've highlighted in red that we're going to use as actuaries. We're going to use the parameter this way as a theta. And one reason for that is when the theta is written this way, the parameter is actually what's called a scale parameter, which again you'll get to later. That's not part of the P exam material, but using the parameter in the way that we use it as a theta here, then it's a scale parameter, and if you use it as the way they have the lambda, it's not a scale parameter. So we're just going to be using the parameter this way. So that's how I'm going to represent the exponential distribution. These are all the facts, or some of the facts that you need to commit to memory with that exponential distribution. Before I get to the gamma distribution, I want to talk about something called the gamma function. And the gamma function is defined this way. It's gamma of alpha is the integral from 0 to infinity of t to the alpha minus 1 e to the minus t dt for alpha values being greater than 0. And notice the point here is that if you look at that integral, t is the variable that you're integrating with respect to. So you're going to take that integrand and you're going to find an antiderivative of that with respect to t, and then you're going to be plugging in an infinity for t and a 0 for t. So the t's are going to go away, and all you're going to be left with is that alpha. So that's a function of alpha. That whole expression there is a function of alpha. You could have just as easily used x as the placeholder variable, and you might have had a gamma of x. And watch what I do in this next slide. I'm just going to replace the alpha by an x. So you could have just had a gamma of x be a t to the, but it's standard notation. It's just standard notation to use an alpha for that parameter. Okay, so again, we're going to use an alpha for that parameter, and let's look at some certain values of gamma, the gamma function. For instance, let's look at gamma of 1. Gamma of 1 is, all I'm doing is plugging in a 1 for alpha, and when I plug in a 1 for alpha in the integrand, the t to the alpha minus 1 becomes a t to the 0, which is a 1, and I'm just integrating an e to the minus t dt, so the an antiderivative of that would be a minus e to the minus t that I'm integrating from 0 to infinity. Plug in an infinity, and you get a 1 over an e to the infinity, that's a 0. So this reduces to a 1. So the gamma of 1 value is just equal to a 1. And I'm going to give you a punchline here that it's an integration by parts argument, but I'm just going to go ahead and give you the punchline. And that is that gamma of alpha will always be, regardless of what the alpha value, gamma of alpha is alpha minus 1 times gamma of alpha minus 1. So if I want to know what gamma of 2 is now, let's use that fact. What's in red is a very important fact, very useful fact. And so gamma of 2, if I plug in a 2 for alpha, will be, well, 2 minus 1 is 1, so it'll be 1 times gamma of 1. And I just computed gamma of 1 as being equal to a 1, so gamma of 2 is also equal to a 1. Gamma of 3, if I go back and again use what's in red here with an alpha equal 3, gamma of 3 would be a 2 times gamma of 2, and I just computed gamma of 2 to be 1, so gamma of 3 is a 2 times 1 or 2. Gamma of 4, with an alpha being 4, would be a 3 times gamma of 3, so that'd be a 3 times that'd be 3 times 2 there is what I should have had there. And then gamma of 5 would be 4 times gamma of 4, and then of course gamma of 4 I just computed to be a 3 times 2, so that's a 4 times 3 times 2. I think I wanted to go far enough so that you can kind of recognize a pattern. Hopefully you can recognize it now that gamma of 5 is 4 factorial. And then I can actually back those other values up and recognize a pattern for gamma of an integer value here. So gamma of 4 is I could have written that as a 3 factorial. Gamma of 3 was 2, but I could think of that as 2 factorial. Gamma of 2 is 1. I can think of that as 1 factorial. Gamma of 1 is 0. I can actually think of that as 0 factorial. So generally, I could kind of extrapolate from this that gamma of n is going to be n minus 1 factorial whenever I have a positive value n. So that's what I really want you to remember from the gamma distribution is that gamma of a positive integer n is equal to n minus 1 factorial. Okay, so now let's talk about the gamma distribution. So the gamma distribution, this is going to be my notation. It's actually a 2-parameter distribution. Again, it generalizes the 1-parameter exponential distribution. So this is a 2-parameter distribution. And this is what the density function is defined to be. Don't get caught up in this right now. I'm going to come back to make a statement about the density function in just a second. All I wanted to do here by showing you this density function is just to show you that if you plugged in a 1 for alpha in the gamma density function, plug in a 1 for alpha, and you'll have an x in the numerator, an x over theta to the first power, but then you'll have an x in the denominator that cancels with that x in the first factor in the numerator, and then gamma of 1 is just equal to 1 in the denominator, and it all reduces to, your density function would reduce to a 1 over theta times e to the minus x over theta, which is the density function for an exponential distribution. So my punchline here is that if you plug in a 1 for alpha on a gamma distribution, you'll get exactly an exponential distribution with that parameter theta. Okay, so that's the punchline that I wanted to get to with respect to this, showing you this density function. Again, I'm going to come back to that density function in just a second and give you an easier way to recognize a gamma distribution from the density function. In past videos, the next thing I talked about was the distribution function, but we're not going to talk about it with the gamma distribution because it's just not it's not a simple rule to follow to calculate the distribution function. So I'm just not going to talk about it. I want to get to the other punchline here, which is that the expected value of the gamma distribution is an alpha times theta. The product of the parameters is what the expected value of the gamma distribution is. So we're using the parameters alpha and theta, and when used in the way that I'm showing you, the expected value is just an alpha times theta, and then the variance is an alpha times theta squared. Okay, so now let's, and I'll come back to this again in just a second. I'll come back in the summary and mention more about these. But for now, going back to this density function, again, I wouldn't memorize that density function. I wouldn't commit that to memory. But what I want to do is I want to recognize that density function is equal to a constant times, so if you take the numerator, let's look at the numerator. Let's look at the first factor in the numerator is an x over theta to the alpha power. Now, the x is the placeholder variable. So I got an x to the alpha from that result, raising x over theta to the alpha power, I'd have an x to the alpha, but then I have an x in the denominator. And so I could combine those two, and that's going to simplify to an x raised to an alpha minus 1. And then I have the exponential factor in the numerator that I'm just going to keep exactly the same. And the point is that all the rest of it, the theta, well, in the numerator, I'd have the x over theta raised to the alpha would give me an x to the alpha over a theta to the alpha. But the theta to the alpha, both of those are parameters, and so that doesn't have an x in it. That's a constant with respect to x, and the gamma of alpha is also going to be a constant with respect to x. So my point is that the density function will reduce to just a constant times x to the alpha minus 1 times e to the minus x over theta. So that's the punchline, is that the density function, I'm putting the symbol up here, that little, it kind of looks like an alpha symbol, but it's really a symbol, a mathematical symbol to say is proportional to. So the density function is proportional to an x to the alpha minus 1 times an e to the minus x over theta. We're going to do an example in just a second, and I'll illustrate how to use this fact. So that's what I personally remember about the density function for a gamma distribution, is that it's proportional to an x to the alpha minus 1 times e to the minus x over theta. And it's defined for x values greater than 0. In fact, the support of the gamma distribution is from 0 to infinity. Okay, so let's look at an example. Let's do this example. A random variable, cap x, has probability density function 125 over 2 times x squared times e to the minus 5x for x greater than 0. What's the mean of this random variable? Okay, so what I'm going to show you first is how I would do this problem. What I would do is I would look at that density function, and I'm recognizing, ignore the constant out front, the 125 over 2. It is whatever it has to be in order for that to be a density function. You know, for that to be a density function, when you integrate the density function over the support, you'll get a 1. So the constant out front has to be whatever it is in order to get a 1 when you integrate the density function over its support. So I'm looking at that density function, and I'm recognizing that that density function is proportional to, in other words, ignore the constant, and it's proportional to an x squared e to the minus 5x, which tells me this is a gamma distribution. And I know that the density function is proportional to an x to the alpha minus 1, e to the minus x over theta. So this is a gamma distribution where the alpha minus 1 is 2 and 1 over theta is a 5. E to the minus x over theta being e to the minus 5x here tells me that 1 over theta is a 5. So I get parameters alpha equal 3 and theta equal 0.2, and then I recall from my, I have committed to memory that the expected value of a gamma distribution is the alpha times theta, and when I multiply those two together, I get a 0.6. That's it. I hope you would agree that that's pretty simple. That's a pretty easy thing to do here to calculate the expected value. Once you recognize that you're dealing with a gamma distribution, and then you know what the parameters are, you figure out what the parameters are, multiply them together, and you got the expected value of that thing. I could have even asked what's the variance, because I know the variance is the alpha times theta squared. I didn't put that in there, but that I could have done variance, easily done variance with this approach. Okay, let me give you an alternate solution, though. One that I think that a lot of people on taking this exam would probably do, and that is to try a direct calculation for the expected value, and use the fact that the expected value is just the integral of x times the density function over the support of the random variable. So you get some integral that you have to calculate that looks like this. So the 125 over 2 I could factor out, and I could combine the x and the x squared, and I'm integrating an x cubed times e to the minus 5x dx. And you probably, I hope you recognize, this is going to be a repeated integration by parts argument. You're going to have to do integration by parts several times. So I hope that you realize the value of the previous approach and being able to recognize the density function as that of a gamma distribution. Hopefully its value is more obvious now, because if you try to use this direct approach, it's just going to be a long problem. Now, even though it's a long problem, I do want to show you a shortcut for doing a repeated integration by parts argument, and this shortcut is called a tabular method for integration by parts. And so what you do is you form a two-column table, and in one entry, the one column, you put, if you were to do an integration by part, you put the u part of the substitution. You would say u is equal to x cubed, and then the dv part would be an e to the minus 5x dx. So you let u be, so on the left-hand column, I'm going to let what u would be x cubed, and then on the right-hand column, I would take whatever the rest of the integrand is, in this case e to the minus 5x. And then the idea with this tabular method of integration by parts is that down the left-hand column you take derivatives, and down the right-hand column you take antiderivatives. So the derivatives of x cubed are 3x squared, 6x, 6, and 0. And when you get to a 0, that's when you can stop with your derivatives. And then the antiderivatives of e to the minus 5x, the simplest antiderivative would be a minus 0.2 e to the minus 5x, and then another antiderivative of that would be a 0.04 times e to the minus 5x, and so forth. Okay, so the next thing that you do with this tabular method is you draw these little diagonals that connect these expressions. So draw the diagonals this way, and then above each of the diagonals, alternate signs plus and minus. So let me explain what I mean by this. When you do this now, what we're going to do is we're going to take the endpoints of each diagonal, and we're going to multiply those expressions together with the sign that goes along with it. And so what we would do then is we would multiply an x cubed times a negative 0.2 e to the minus 5x, and we would take the positive product of that. And then we would take a 3x squared times a 0.04 e to the minus 5x and take the negative product of that. And we would do that for each, all the way down the table, and then add all those values up. So I factored out the 125 over 2, and when I take the signed product of the endpoints of the diagonal, that's gonna, and I add them all up, that's gonna give me the actual expression for the integral there. So that's the tabular method for integration by parts. And then, of course, I'm integrating from 0 to infinity, so I have the evaluation of this expression from 0 to infinity. I've made this comment a few times before in other videos also. If you look at what's in the parentheses there, every term is negative, and I don't like all the negatives, and you're going to plug in the upper limit of integration with all these negative expressions, and then you're going to subtract off what you plug in with, the lower limit of integration plugged in with all the, I don't like all those negatives, so I'm going to change the signs of all those expressions, and I can account for that by interchanging the limits of integration. So that's what I've done on this expression. And now at this point, what I want you to notice is that if you plug in a 0 for x, then every term in the parentheses has an x in it, except for the last term. So when you plug in a 0, all the terms are 0 except that very last term, and that very last term I get a 0.0096 times e to the minus 0, which is just a 1, so I just get a 0.0096. And then when you plug in infinity, all those e's have a negative exponent, and so e to the minus infinity is 0, and not only is it 0, but it dominates the infinity raised to a power is dominated by an e to the minus infinity. E to the minus infinity is 0. Infinity raised to a power. Even though it's an infinity, it's being dominated by the 0. That's the that's the exponential. And so the result here is that when you evaluate this, you get 125 over 2 times 0.0096, and that product is, lo and behold, it's 0.6. Same thing that I got before. And that was the way I got it before was, again, looking at the density function and recognizing that it was proportional to, an x to the alpha minus 1 times e to the minus x over theta, and that's a gamma distribution. Okay, so finally the last slide here is a summary. So you have a gamma distribution that has parameters alpha and theta. The support of a gamma distribution is 0 to infinity. The density function here is proportional to the x to the alpha minus 1 e to the minus x over theta. And then the expected value is an alpha times theta, and the variance is an alpha times theta squared. Plug in an alpha equal 1 if you have a gamma distribution with a parameter of alpha being 1, you really just have an exponential distribution at that point. That's what's called an exponential distribution. Here are all the facts with the exponential distributions. Notice that the expected value of the exponential distribution is theta. If you look at the expected value above and plug in 1 for alpha, you get theta. Likewise with variances, plug in a alpha equal 1 for the variance of a gamma distribution, and you get the variance for the exponential distribution. You get all the same parameter values. And then the last thing I wanted to recognize or mention is that in the bottom left here, I mentioned what the survival function is for an exponential distribution, just because I want you to be able to recognize that. So if you're given a survival function in a problem and and it's an exponential function, then you're just dealing with an exponential distribution, and then you take whatever the coefficient of the negative x is in that exponent, and you take the reciprocal, that gives you the theta. Okay, exponential distributions, again, probably the most commonly tested distribution on actuarial exams. So please commit all of this to memory, and you'll do fine on these problems. All right, I'll see you in the next video.